Hi, in today's video I'm going to go over one type of reaction that occurs commonly with aldehydes, and that is the hydration of aldehydes. So water can act as a nucleophile and attack the carbonyl group as well. But what we know about water is not a strong nucleophile. So that's going to mean two things. One, hydration of a ketone is not favored. So if I were to try to react water with a ketone, so say I just got a simple ketone here with acetone, react it with water, and this would be my hydrate. So this product here, this is called a hydrate. In this reaction, you're looking at greater than 99% with the ketone. So the reaction strongly favors just keeping the ketone. However, the hydration of an aldehyde, and specifically a very simple aldehyde like formaldehyde, is favored and is strongly favored. So now if I'm reacting formaldehyde with water, and notice all of these are equilibrium reactions. When you have a weak nucleophile like water, its reaction with a carbonyl group is always going to be in equilibrium. So this time when I'm forming the hydrate, now greater than 99% of the product will be the hydrate. Now, why does it work for something like formaldehyde but not for a ketone like acetone? The key is in the methyl substituents they have in the ketone, or the R groups, whatever you're going to have in your ketone. Right? These methyl groups each have 3 hydrogens on them. So there is a lot of electron density going on. Right? You've got 3 hydrogens here, 3 hydrogens here. You have your oxygen with a hydrogen on it. So there's just a ton going on. There's going to be a lot of steric hindrance. I only have 1 hydrogen for each of these bonds. So there's a lot less electron density, and there's a lot less steric interactions between the 4 substituents in the hydrate that comes from the formaldehyde versus the hydrate that comes from the ketone. So that's why it's favored for the aldehyde, but not for the ketone. Now, there's 2 ways you can catalyze the reaction. It's going to proceed very slowly if all you do is just stick formaldehyde in water. So you can either catalyze it with an acid or with a base. So acid-catalyzed hydration, you'll start with your formaldehyde, and you have a strong acid. So H2SO4, for example. So now you've protonated that carbonyl group. And remember, the protonated carbonyl group is in resonance with a carbocation. So this really adds to the reactivity of your compound. So now this will react again in equilibrium. Oops, drew the arrows the same direction. So this will react in equilibrium with water. So nucleophile comes in at the carbonyl carbon. So now I've installed both of the oxygens. The last step needs to be to deprotonate that group that just came on. And that deprotonation is just going to happen with another water. Because we're in acidic conditions, right, we can get hydronium. You'll notice when we go to basic conditions, the deprotonation and the protonation steps occur with different reagents. So that is the acid-catalyzed formation of a hydrate. The base-catalyzed is one fewer steps than the acid-catalyzed one, because this time we're using a strong nucleophile, and that strong nucleophile is hydroxide. It is our base. So we don't need to protonate the carbonyl oxygen before the nucleophile attack, since now we have a strong nucleophile. So the hydroxide comes in, and then this time the protonation, we're again in equilibrium here, so I want to make sure we know that. Same thing with this step, is in equilibrium. So water, it's amphiprotic, right? So this time it can act as an acid, right, rather than acting as the base. And we get our hydrate. Now, a couple of important notes from the acid-catalyzed and the base-catalyzed. You should never have a negative formal charge in an acid-catalyzed mechanism. Right, in our acid-catalyzed mechanism, it was all positive formal charges. We never had a negative. For a base-catalyzed, you can never have a positive formal charge in base-catalyzed. Right, because a positive formal charge is indicative of something that's a strong acid, right, or stronger acid, which you're not going to have in basic conditions. So when you're making mechanisms, not just for hydrate formation, but as we move forward with reactions of ketones and aldehydes, and in general, in any organic reaction, if you're in basic conditions, you should not have any positive formal charges in your mechanism. If you do, you have to look back at your mechanism and see where you went wrong with it. Same thing with acidic conditions. You find a negative formal charge. You made a mistake somewhere in your mechanism, so you want to go back and look for where you made that mistake.